right. This is a long state wire which carry a current 10 ampere from left to right. An electron above this wire 1 centimeter above from this wire is traveling towards the right at a speed 1 into 10 to the power 7 meter per second. Then what would be the magnitude and the direction of the magnetic force on that electron? We have to find out the force acting on that electron. Fine. Let's start. We can find out the force, magnetic force on the charged particle electron using that formula that given. Fm, subscription M stand for the magnetic force, so Q, which is the charge, into V cross B. V is the speed of that charged particle and B is the magnetic field at the location of that charged particle. The speed of the electron is given, which is V is 1 into 10 to the power 7 I hat meter per second. I hat because say I'm choosing, say this is my positive I direction or positive X direction, and say this is actually J hat, and we can also consider say that the K hat actually out of the screen. Say this is actually the dot. This is actually the K hat. Then we can say that the V speed of the electron towards that positive X direction. That's why it's 1 into 10 to the 7 I hat. Fine. Now what would be the magnetic field B, which is going to produce by the current into that wire? The current into that wire. We know that the magnetic field is for a long state wire is going to be given by the magnitude actually V actually mu naught I divided by twice pi R, where I is the current through that wire and R is the perpendicular distance from that wire to at the location of the magnetic field. Fine, it's a magnitude. I have to find out the direction of that field also, because magnetic force is a vector which is a cross product, right? B cross B. To find out the direction of this magnetic field for a long state wire, what I'm going to do, I'm going to use the grip rule. What is that grip rule? I will place my, say that the thumb towards the direction of the current. Say I'll place my thumb towards that direction, and I will rotate my rest of the finger around that wire, If I do that, then the rest of the finger, the direction of that finger will give me actually the direction of the magnetic field in different point. It's a three-dimensional case, remember, because we know that when a current actually the following through the wire, around that wire magnetic field is always tangential to the path. Say for example, say this is a wire, say the current into that wire is basically out of the screen. Then if I choose a Gaussian surface around that wire, then the magnetic field in any point in this Gaussian surface, it will be always tangential to the path. So if you think about at the top point, it should be towards the leftward. If you think about that point, it should be the downward. If you think about that point, it should be rightward. And if you think about that point, it should be the upward. That means it's always tangential to the path. In every point, it should be tangential to the path. Now think about that case. Since this is also you can find it using the grip rule. Put your finger out of the skin, because current is out of the skin, then rotate your finger around that wire, and every point rest of the finger will give you the direction of the magnetic field. Using that idea, we can find out that the magnetic field above on this wire, it will be basically out of the screen, or you can say that means it should be basically at the top of the wire, it will be out of the skin, and at the bottom your finger will be basically into the skin. So that's why at the bottom the magnetic field would be basically into the screen, and the above the magnetic field would be out of that screen. Fine, I find out that direction also of this magnetic field. Now I can find out that the magnitude of this one, because I know the everything. So the B would be, in that case I could find out, say mu naught, actually the 4 pi into 10 to the minus 7. I is the 10 ampere, that's given, and radius, so that's mean the location of this electron, which is actually that 1 centimeter, right, is traveling. Then 1 into 10 to the minus 2 meter, I convert into that, into the meter. If you solve, then the magnitude of this magnetic field would be 2 into 10 to the minus 4 Tesla. So this is actually that magnetic field strength. Now we are going to find out the force on that electron, which is actually above that wire. Then I can say at the location of this electron, the magnetic field would be basically out of that screen. Since I give out of the screen actually the k head, then I will write it should be that 2 into 10 to the minus 4 k head into Tesla. So this is my magnetic field at the location of that electron over here. Because I choose my reference axis, actually out of the screen is basically the positive z axis. Fine, now I could find out the force. What I will find, that force actually on that electron would be charge, is the charge of this electron, which is minus 1.6 into 10 to the minus 19. This is the charge, right, into, I have to use the cross product V, which is 1 into 10 to the 7 I hat cross the magnitude of magnetic field, which is 2 into 10 to the minus 4 k hat, right? Then I can find out what would be that. If you do that, you will find out F into A is going to be the minus, if I multiply that one, it should be basically 3.2 into 10 to the minus 16 into I cross K. Now we have to use the properties of the unitary vector, right? So I cross K, because we know that it's a, if I take I, J and the K, I cross J, that will give me basically the plus K. If I write down the I cross J, it will give me the plus K, since it's a counterclockwise. But if I write down J cross I, that means the clockwise, I'll find out minus J cross I, I'll find out the minus K. Now over here I'm taking the J cross K, right? Sorry, I cross K. I'm taking that I cross K, I'm moving to the clockwise, then I'll find out the minus J. So that's mean I'll find out, so this Fm would be minus 3.2 into 10 to the minus 16. I cross K would be basically that minus J. So then I can find out the force. This is going to be basically plus 3.2 into 10 to the minus 16 Newton J head. So that's mean at the location of that electron, the force on that electron due to the current into that wire would be basically 3.2 2 into 10 to the minus 16 j hat. So that's mean the force on the electron would be basically that upward, because this is my positive j hat direction. So that's with the force on that electron due to the current into that wire. Thank you very much.